and then you're going to be officially done with the class. Yeah. So what we're doing today is going through this here and kind of going over some of the topics specifically. I have a feeling the first one on the list is and the main things is going to be addition, subtraction, multiplication, because I feel like y'all are comfortable with all three of these here, addition, subtraction, multiplication. Because addition, subtraction, multiplication, we can type it into the calculator, it'll do it for us, because it's just combining like terms. So the numbers without I, we would add or subtract. The numbers with I, we add or subtract. With multiplication, we just distribute it out. If I has a power greater than 1, we reduce it. Because our versions of I are I, negative I, well, it would be I. I'll put them in the correct order. Because it's I, negative 1, negative I, 1. It's kind of the four values of I that we have. We can't have I to a power greater than 1. With division, we can't have I in the denominator, and the only way to simplify that is to multiply by the conjugate. The complex conjugate. So we just change the sign in front of I and then multiply that on top and bottom to get the denominator to not have I anymore. Yeah. Yeah. So that's the big thing with division. For the most part, if it's asking us just to find the solution, we can type it into the graphing calculator, the 30x or the 84 plus CEs. We can use alpha y equals and do it. But again, if we're having to do it by hand, we've got to multiply by this complex conjugate. Yes, because if we had 4 over 3 minus I, we would multiply top and bottom by 3 plus I. The numerator, 4 times 3 is 12, 4 times I is plus I, 4I. The denominator, 3 times 3 is 9. 3 times I is going to be plus 3I. Negative I times 3 is negative 3I. And negative I times I is negative I squared. Well, those cancel. Well, I squared is the same as negative 1, so we have 9 minus negative 1, which is 10. At this point here, we can simplify because they all have a common factor of 2. We would have 6 plus 2I over 5. Rational equations, and again, when we solve rational equations, one of the biggest things is you got to get the denominators to be the same if we're going to add or subtract. If you add or subtract rational expressions, the denominators have to be the same so we can add or subtract. If we're solving, we need to just multiply by a single number or term across everything just to get the denominators to cancel, and then we can solve from there. So x plus 7 over 4 equals 9 over 2x. I have no idea what this is going to give us. Because if I wanted to solve this here, we're going to multiply everything by 4x. I'm not intentionally not using 2, but here the x and x would cancel. Here the 4 and 4 would cancel. And the last one, the x and x would cancel, but 4 over 2 would reduce the 4 to 2. So it would reduce all of the terms. And what that leaves us with is 4 times 2 is 8. plus 7x is equal to 18. 7x is equal to 10. X is equal to 10/7. Yes. And the nice thing with multiple choice tests and equations is that you can plug values in to see which ones work. Quadratics. What is one of the key things that will tell us that an equation is a quadratic? If it has what? X squared. If it has x squared, it's quadratic. If it has x cubed, it's cubic. Kind of a giveaway is that it has x squared. And one of the equations to know is our quadratic formula. And just how it works with our formula, where A, B, and C are, and how to plug it in. It'll be good to know. Because for the most part, as long as the quadratic has integer solutions, we can graph it and find it. If it has rational solutions, we'll have to probably factor or use the quadratic formula. If it has irrational or complex solutions, we're going to have to either use the quadratic formula or complete the square. Any questions on these so far? Kind of pretty straightforward. Inequalities, rational and linear. I don't think we need to talk too much about inequalities. Inequalities are very similar to solving equations, especially linear inequalities. So we could say 7x plus 14 is less than or equal to 2x plus 9. All we got to do is get x by itself and solve from there. If we can keep the number in front of x positive, that's going to make everything work a little bit nicer. This is a miracle. Because then we'd subtract 2x from both sides. Minus 5x is less than or equal to negative 5. Divide both sides by 5. And we have this here. So it's telling us that negative infinity, comma, negative 1. If we wanted to do a interval notation, graphing, we can do anything from there. So are we saying x is bigger or less than negative 1? So which way are we going? To the left or to the right? We're going to the left to negative 1, yes? So which one's left? Yeah. It's just sometimes if you need to, because we could graph it on a number line. We're going to the left? Okay. Negative infinity. Questions on these here? For rational inequalities, the main thing I will say with this here is just get it on the same side and then solve from there. Add them together and then see what's going to make the numerator be 0. And do that. So, I mean, just get them on the same side of the equal sign. you know. So for the most part, well, we can see what's going to make the numerator be 0. Well, that's just, so here we have x minus 3 is greater than or equal to 0. Add 3 saying x has to be greater than or equal to 3. The denominator is just telling us that x cannot be 1. Well, that's not an issue because all the values that work for this here are greater than or equal to 3. So we have no problem there. So since we're talking about greater than or equal to 3, 3 comma infinity. If that restriction had come into play, we do have to just take it out. So if it had been, say, 4, we'd done bracket 3 comma 4, parentheses union 4 comma infinity. Okay. We good with this here? We're kind of understanding of what we're doing with these. Symmetry, symmetric to x, symmetric to y, and origin. So if it's symmetric to the y-axis, it's really just flipped across the y. So most quadratics, y equals x squared. Same on the left and right side of the y-axis. It's symmetric to the y-axis because it's flipped across it. Symmetric to the y-axis. If it's symmetric to the x-axis, it's kind of the same on the top and bottom of the x-axis. And if it's symmetric to the origin, it's kind of the same either way. Kind of like a linear line, symmetric to the origin, going across. I don't think we have to say much about the horizontal or vertical line tests, because horizontal line test is testing if it is one-to-one. Vertical is testing if it is a function. So if we can draw a vertical line up and down and it crosses in more than one place, it's not a function. Horizontal, if it crosses in more than one place, it's not one-to-one. It doesn't have an inverse. Domain and range. Domain are our x values. And do y'all remember which two types of functions would have restrictions on the domain? Because there's only really two. They are, radicals, where n is even, or rational. Now, it's not going to be every root, nth root that's even, because as long, I mean, we could take the square root of x squared plus 1. We would still have values that work. But if there's a case with even roots where we can have a negative inside the radical, we won't have the entire real number system. It's whatever is going to make that be 0, or not 0, but be negative. Rational. We have to remove anything that would make the denominator be 0. So those are the only two functions where the domain's not all real numbers. Because any polynomial function, where we don't have x in the bottom of a fraction or fractional exponents, the domain's all real numbers. Quadratics, cubics, quartics, all real numbers. Equations of lines, all real numbers. Absolute value, all real numbers. Exponentials, all real numbers. And actually, as I'm saying that, if we look at logarithms, what's inside the log cannot be 0 or negative. So those are the three, really, that we do have restrictions. And if you do have questions or trying to figure out if they do have restrictions on the domain, graph it. Graph it. What's inside here? Because we can't take log of 0, we can't take log of a negative number. So whatever values of x would make what's inside the log be 0 or negative, have to be removed. It has to be bigger than it. Range. Range is what? The y values. So especially looking at the domain and range, graph it, see what you get. So the y values on the y-axis, which y values are covered? And with the equation of a line, it's going to be all real numbers. Any odd degree polynomial function is going to be all real numbers. Increasing and decreasing. I didn't write it, but we also have constant. Well, increasing should be exactly as it sounds. That's where the function's going up. And we always read it as we would read a book. We read a graph from left to right. So as you go, especially looking at increasing, decreasing, I would start at the farmost left point that they give you on the graph and go from left to right. Is the graph going up? Is it going down? Or is it constant? And the values, and again, all of these are listed on the x values. So we're talking about the x values. Is it increasing, decreasing, or constant? So we list them kind of as the range. Range of x values where the function is increasing, the range of the x values where the function is decreasing, or the range of the values where it's not changing, the y values. Does that make sense? Because essentially we're looking at what is y doing, and we will determine it or list it as increasing, decreasing, or constant based off the x values that correspond to those given y's. Factors. I think we feel pretty good with factors, factoring, because if it is a factor, it means it's a solution. It's going to make the function equal 0. So with a lot of those, if we're determining if it's a factor, we can do synthetic division, we can do long division, either one, and if it's 0, then it is a factor. Essentially get x by itself, because if they ask to say, is x minus 3 a factor? Well, really we're saying what? X is equal to 3. We would set it equal to 0, solve it. So we're trying to say, is 3 a solution? We can plug it into the function and see, do I get 0? If I replace every x with that value and get 0, it is indeed a factor. If not, it's not a factor. Because we can do that with synthetic division, long division. I think y'all feel comfortable, especially with synthetic division. And I know that there's at least one of those on the test if you do have questions specifically. Huh? If, especially trying to determine factors, we can do synthetic division to find it, or plug it into the function, or graph it and see. Higher degree polynomial functions. Well, the main way we solved most of those was.
Can I have your attention, please, teachers? Don't forget to do your left count. Thank you.
Well, if you all remember, the main way that we do higher degree polynomial functions was first try to factor it for the most part. Well, the book and a lot of people say, I mean, if we can factor, we try to do it first. If not, we normally go to graphing. So for a lot of higher degree polynomial functions, I would graph it first, get the solutions, then do synthetic division to simplify it from there. Because if we had, say, a 4th degree polynomial function, and I get 2 solutions, I know I need how many? 4. So we can use synthetic division to reduce it down. Questions on polynomials, higher degree polynomials, and solving those? We feel kind of good with that. Especially, I mean, looking back over the test, we do have some there to kind of revisit, go back over that. Function operations. Well, these here are kind of straightforward. F of x plus g of x, f of x minus g of x, f of x times g of x, and f of x divided by g of x. With any of these here, f of x plus g of x, we replace f of x and g of x with their function, and since it's addition, we add like terms. F of x minus g of x, we replace f of x and g of x, and then subtract the two. Multiplication, we replace f of x and g of x with their functions, and then multiply them together. And f of x divided by g of x, we replace them with their functions and then simplify if possible. If they have any common factors, we would simplify those out. The only other function operations that we have is our f of g of x and g of f of x. And as I've always said with these here, work your way, bless you, from the inside out. So the first thing you would do is plug x into g of x, which is just going to end up replacing g of x with its function. And then take that entire function and replace every x in f of x with that function, and then simplify from there. I'm going to write it down here. I know that most of y'all, I don't think you need a reminder of what the slope formula is. y2 minus y1 over x2 minus x1. Change in y over change in x, or distance. Square root of x2 minus x1 squared plus y2 minus y1 squared. And with the distance formula, just make sure the x values are together, y values together. We'll get the distance formula. I think we're good on slope and distance. I mean, midpoint, well, I'm just going to throw it up there just so we have it. Midpoint formula, x1 plus x2 divided by 2, comma y1 plus y2 divided by 2. Now with distance and midpoint, it really doesn't matter the order of x and y as long as x and y are together. The only one of these three formulas where the x and y spot matters is slope. So whichever y value you put first, its x value has to go first. We have to keep them in order. The others, it really doesn't matter. Questions on any of this so far? I don't think we need to go too deep in lines. Equation of a line, we can graph it. Y equals mx plus b. As long as we have the slope and y-intercept, we have it. I will go on. Why don't I just go on and give you because I have a feeling most of these equations y'all don't have as readily available in your memory as I do, mainly because y'all haven't done them as long. But this is slope point form. So as long as we have a point in the slope, we can find the equation of the line. We just have to plug it in and then get y by itself. Inverses. Rewrite f of x as y. Switch x and y. Solve for y. Rewrite y as f inverse of x. These are the four main steps to inverses. The only ones that get tricky are rational inverses. Because with rational inverses, we have to multiply both sides by the denominator. Then we have to get y by itself. So we have to group them, get everything to the other side, factor the y out, and then divide. We good with this here? f inverse, f to the negative 1 x. Now the f inverse and f of x is just a term. I'm just using those if the function starts out as f of x equals the function. If it was g of x equals, it would just mean the two places that we have f of x and f inverse with g of x and g inverse. I'm just using f of x because it's commonly used for most functions. Now we can do it with g of x, h of x, z of x, q of x, y of x, because they chose to use y, but we can do any of these here. So we feel kind of comfortable or kind of remembering most there. So again, I would go back more in depth, or at least look back over some, because I know the test we did have inverses, kind of going back, refreshing your memory on these. Logs to exponents, exponents to logs. What we're talking about is our y equals log base b of x is true if and only if b to the y is equal to x. Now my arrangement of x and y have changed depending on how I started the problem or set it up, but the overall statement still holds true on how we change from one to the other. Being able to remembering how to switch between one and the other, going from exponential to logarithmic and logarithmic to exponential. Or if you want to use the properties of logarithms we were in about solving it to go from one to the other, that still holds true. Because for the one on the left, I could put both sides to the base of b. That cancels, leaving me with x is equal to b to the y. Or the same thing is true with going the other direction. For b to the y equals x, I can apply log base b to both sides, which would indeed give us y by itself is equal to log base b of x. We can go from one to the other. Properties of logs. Log base b of m times n is equal to log base b of m plus log base b of n. Log base b of m divided by n is equal to log base b of m minus log base b of n. And lastly, log base b of m to the n is equal to n times log base b of m. These are the three main properties of logarithms. If we're expanding, we always kind of go in the order of division, multiplication, powers. When we're condensing, I always go powers. I take negative as an exponent. I will pull the negative up into the exponent. And then multiplication and reducing from there. As a reminder, especially with fractional exponents, if we take a fraction up into the exponent, do reduce it back to a radical, back to radical form. And I'll put that up here. The nth root of a to the x is equal to a to the x over n. So that might be good to know as well. Questions on this so far? Solving systems. There's two main ways, well, there's several different ways. Elimination, substitution are the two main ways to do these by hand that we went over, especially with linear and quadratics and any of these, well, mainly linear functions. Substitution, you just need to get a variable by itself. And then plug it into the other equation. So we want to get one variable by itself, solve it for that variable, plug it into the other equation, and then we can solve to find whichever one it is. So if we got y by itself, we would plug it into the other equation for y, solve for the value of x, and once we find x, we go back. Elimination. Get one variable to have the same number in front. And then eliminate it. Add or subtract. If they're both positive or both negative, we subtract. If one's positive, the other's negative, or vice versa, we add. Substitution and elimination. Because otherwise, if we're just asked to solve the system, we do have other ways that are a little bit faster, a little bit easier. Because we can use reduced row epsilon form we saw with our quadratic, not quadratics, our matrices. We get it into a matrix form, get x, y, and z on the left-hand side, plug it in, and do RREF, and it would solve the system. Or we could graph it and see where they cross or intersect. Questions on any of this here? All right. Rational asymptotes. Vertical. Whatever's going to make the denominator be 0 is going to be a vertical asymptote. Not every single rational function will have it because there are some times where there's no way to make the denominator be 0. But that's one of the good places to start, especially if you're trying to graph a rational function, is start with the vertical asymptotes. Horizontal. If the degree of the top is greater than the degree of the bottom, there is none. There is no horizontal asymptote. Because we do not have horizontal, we have what? Slant. Because if the degree of top is greater than the degree of the bottom, we have a slant asymptote. And we have to do, you can do synthetic division or long division. And whatever we get from it, not the remainder, but what actually the quotient, I believe, we get from it is the slant asymptote. If the degree of the top is equal to the degree of the bottom. Leading coefficient over leading coefficient. Number in front of the variable with the biggest exponent divided by the number in front with the biggest exponent. And we could actually say y equals leading coefficient over leading coefficient. It's going to be a horizontal line wherever those two are divided. So if the top one was 5x cubed, the denominator was 6x cubed, the vertical or horizontal asymptote would be 5 over 6. And lastly, degree of the top is less than the degree of the bottom. Y equals 0. And if you're having to graph, those are really graphs of logarithms or exponentials. It's not graphs going from one to the other, it's just graphs of one or the other. I would graph it, see what we get. Are we good with polynomial division? Because that's long division, synthetic division. Polynomial multiplication. Polynomial multiplication, that's just multiplying two polynomial functions together. We use our distributive properties. I think we feel good with those. Solving exponentials. So that's using our logarithms, especially if we have variables on one side, or getting them to be the same. Also, let me finish these and I'll let y'all head out. Especially if they give you answers, plug them in, check them. That's the easiest way, especially on a multiple choice test. Plug those answers in and see if they work. If they do, they are the correct answer. If they don't, they are not. And you can do that with any equation. Exponential, logarithmic, linear, quadratic, absolute values. Plug them in for every x or y and see, does it give me a true statement on both sides? If it does, that's the solution. Possible rational zeros. This is our plus or minus p over q. Where p is all the factors of the constant term over all the factors of the leading coefficient. I have no idea if I spelled coefficient right, but that's fine. Y'all know what I mean by it. is how we find all the possible rational zeros. So if the constant term was, say, 12, 1, 2, 3, 4, 6, and 12, no, because 1 and 12, 2 and 6, 3 and 4 are going to be the factors of the constant term. And we know one of the leading coefficients factors has to be 1. So we should have 1, 2, 3, 4, 6, and 12. All the factors of the constant term should be there as integers before we even start doing fractions. And when doing any of these here, just like with any multiple choice test, kind of be keeping an eye on the answers, like we said with the ACT. If one of them, for say, constant term was 12, if 2, 4, 6 are not included on one of the choices, it's not it. And that might help you eliminate some and go from there. So that way you're not having to find every single possible factor for some of the bigger ones. Graphs of rationals. Just graphing it. I would use the graphing calculator and use asymptotes. Vertical asymptotes, horizontal asymptotes. I would find the asymptotes first and then kind of match it up because, again, you're not having to physically graph. It's all multiple choice. Use the asymptotes to kind of narrow it down which one it is, and then you can use the graphing calculator to take it from there. We kind of good with this here, yes? Matrices. I don't think I have to say too much on matrices. We feel comfortable with those. And lastly, Cramer's rule. Because Cramer's rule, when we find x is equal to the determinant of this here. Now, we normally called, especially on the homework, they called the determinant of the denominator of each variable d, matrix D, or determinant of matrix D. So that might be something to be aware of. And for the numerator, whichever variable we're replacing, so here I'm acting like it's a 3 variable, we replace the x values for this one here with what it's equal to, y's or c, and go from there. Any questions on any of this here? If you do, especially going over the review sheet, there's something that you see that you would like to have more information on or more specification on, please ask. I would go through the old tests and kind of look at each of those parts and see and kind of reference back to those there. Okay? If you do have any other questions this weekend, please email me. Your test will be